Welcome and good afternoon. I'm Joel Abramson, member of faculty here at the Grad School of Education. We're very glad to have with us today Dr. Ido Roll from the University of British Columbia, Vancouver, where he serves as the director of the Institute for Scholarship of Teaching and Learning. Yeah, it really does. Dr. Roll graduated from the Human-Computer Interaction Institute at Carnegie Mellon University and later was a researcher at the Carl Wyman Science Education Initiative and the Department of Educational and Counseling Psychology. And let me read a bit from the blurb Ido sent us, which captures his research interest so succinctly. Ido studies how interactive learning environments support students in becoming more competent, curious, creative, and collaborative, normal C word, learners in classrooms and online environments. His work focuses on cognitive and non-cognitive factors across different time scales, from minutes in problem-solving environments and simulations to months in MOOCs and learning management systems. His research employs methodologies from the fields of education, cognitive science, learning analytics, and human-computer interaction. End quote. Recently, I had the pleasure of interacting with Dr. Roll around a special issue of the journal Instructional Science, so this is a plug, on discovery-based learning, which I co-edited with Manu Kapoor. For this special issue, Ido's team authored a paper on science educational technology with the impressive title, Understanding the Impact of Guided Inquiry, the Relationship Between Directive Support, Student Attributes, and Transfer of Knowledge, Attitudes, and Behaviors in Inquiry Learning. So there we have a shorter title on the benefits of being lost when supporting exploration leads to better learning. So let's all get lost together and join me in welcoming Ido.
Oh, I should have put the let's get lost
together.
No, what's his name? Chet Baker.
Oh, good. So welcome.
Thanks. Hi everyone. Thanks for the invitation. Glad to be here. Speaking of, yes, I'm not good at titles, but what we did once, and I encourage all of you, and we created haiku summaries of our research. And it is really interesting to try to summarize your research into a haiku. You have to know what you're doing to be able to do it. It's a fantastic challenge and it's fun to share. So yes, as Dor mentioned, most of my work is about online learning, how we make online learning more meaningful and less technical, procedural, mechanical. But also, as Dor mentioned, he just edited a really interesting special issue in Instructional Science about the discovery-based learning. So, to which we contributed a paper, which made me think, actually, what do I have to say about discovery-based learning? So, this is not actually a lot of the bulk of my work. This is kind of more of an opportunity for me to reflect and to keep myself busy on the flight and to think how different things fit into sense-making in discovery-based learning. So it's a lot of sense-making, and specifically about being lost. And I think that I'm a little bit preaching to the choir here in the big instructionist, constructivist debates, because I think, relatively speaking, the school here is pretty much in the constructivist side of the spectrum. But what I want to focus on is actually, yes, there is value for guidance. It just may be after some exploration, merely for novices. So what I kind of want to make the case is for the benefit of exploration for novice learners. And let's see if that works as good as a clicker. Yes, so I think, and I'll just grab my glasses. This is common wisdom that I think we all agree with, that novices learn more when they have support. Experts don't need as much support. Right? Wood put it in the scaffolding, original scaffolding paper, and revisited that nicely in 2001. And Carl Yoga talks about the expertise reversal effect. The expertise reversal effect is essentially an attitude treatment interaction. It shows that instruction has differential effect based on students' knowledge. And specifically what Carl Yoga says is that novices need more support. But when we give that much support to experts, it actually hinders learning. So novices need a lot of support, experts need little. And that's kind of the two broad themes of this that I think are pretty common. But there's also a fallacy that often follows, and that support means hand-holding and guiding. Support means telling students what to do. And actually, Kaluga himself talks a lot about this form of support as being guidance. And maybe the clearer example of that, an implication of that is that without guidance, it means we provide no support. Right? That we can be irresponsible by not guiding students, not telling them what to do. And of course, the ultimate strawman here is a Kirshner-Swirler-Clark paper that equated minimally guided with problem-based learning and inquiry learning and experiential learning and everything together as, oh, we don't support our learners. Which we support in many ways that are not guidance. So a slightly more nuanced and nice term is what Guidande and 11 called assistance dilemma. And they define assistance dilemma as how should learning environments balance information or assistance given and withholding to achieve optimal student learning. Right, so we still have information, but information could be many things. Plus we have assistance, which goes beyond information. And this concept of assistance dilemma, I think, is very rich and helps us work with, because it introduces questions such as, well, what kind of support, and when, and to whom do we offer it, and in what context, and for what purpose. Different types of support will lead to different types of learning outcomes. So it is indeed much more nuanced. So I'll start with the conclusion slide in case you guys ran home early and it will help us frame the discussion. So one thing is that learning from guidance is hard. We again think that guidance is easy, is there to reduce cognitive load. I actually think that guidance quite often imposes cognitive load. Because not only we have to understand the basic activity, we also need to understand the guidance of the instructions that are given. Also, often guidance does not support transfer of knowledge. Because if I'll tell you what to do in one context, how can you learn what to do in another context? Because there's no more, because the guidance doesn't apply there quite often, as I'll show. The other thing I want to talk about is how novices are actually especially challenged by guidance. Because of the limited prior knowledge and experiences, they don't have what to build on in order to interpret guidance. And again, a separate guidance from support. I do advocate for support that doesn't take the form of guidance. So what support should do? It should facilitate the process in which learners actively explore their ideas, make sense of the outcomes prior to guidance, we'd say, prior to instructions. Right, so what I want to focus on, again, is this phase of exploration and sense-making that precedes guidance. And I'll do it in three contexts. The first context will be physics labs, online virtual labs, where you build circuits and have lots of fun. The second one is quite the opposite. This is the Geometry Cognitive Tutor, a very constrained problem-solving environment for geometry. And the third is the Invention Lab. This is a system that supports invention, productive failure activities for middle schoolers. I'll go into more detail with each of these. And if you want to dive deeper into each of these, because there'll be a bit of a survey, then please feel free to ask me later. So let's start with the physics simulations. And that work that was done mainly with these fantastic people, the Butler, Doug Bond, Sarah, Nikki, and Jonathan, all from UBC, and Kathy is from Boulder. So PhET simulations are a family of simulations, about 120 of them in different STEM topics, different ages. About 85 million runs a year. And so far, no single data file collected, almost no single data file, which to me is a huge crime against education. So we put the data in that and we collected 100 log files. We instrumented one of the simulations, collected 100 log files. But this is how learning looks like. And this is authentic movie from students. Sped up, of course. Students put circuits. They can create fire if there's short circuit. They could put lights and batteries, and soon they'll put measurement instruments, as you'll see. I think that this could, there's a voltmeter to check different things. So it's really an open-ended environment, in this case to build circuits. And that is the most commonly used simulation out of the 120 simulations I mentioned. Highly recommend. They're really fantastic. And for example, my kids love playing with them, and that shows kind of the value of this inquiry. So this is my daughter and my son, and they had a bunch of friends over, and they practiced rubbing balloons and showing how the balloons get stuck on them. And then immediately afterwards, my kids took everyone to the computer to play with the PhET static electricity simulation, right? So we actually see some transfer there. And another example, this is my son and his friend, and they had orange juice that was too sweet. So my son tried to explain his friend, there were 5 here, yes, there were 5 here, why adding water to the orange juice will make it less sweet. And he tried to explain it using concepts and intuitive ideas that he had in the concentration PhET simulation. So this is very rich and authentic inquiry that transfers to the real world. It's commonly used, and for example, one place it's used, it's mastering physics. That's a very widely used Pearson homework platform for college. Probably used here too. And this is what how Pearson uses PhET. Select, show if you agree, drag one positive, select, show numbers, with a sense of one away from, one is one meter away. So it doesn't really make good use of this rich environment. And so it really takes the opposite extreme of let's really guide everything the students do. And essentially kill all joy from learning as we do that. So we wanted to compare not as extreme, but slightly 2 versions of this. We took 100 students, roughly gender balanced, from 2 physics courses on campus at UBC, 100 hours a day, 130,000 actions. And these are just pictures of me going between students, taking pictures of them. You can see different strategies that they use. You can see the compare and contrast here. And the students who got kind of just go the playful side of making fires by seeing how many batteries can be changed before fire starts. And we see different versions. And the study happened like that. And that is where I apply or demand too much cognitive load. So bear with me for a slide and a half. We gave students, all students, a learning goal, a learning outcome for 20 minutes. The learning outcome was use a DC circuit PhET simulation, that is the simulation you saw, to explore how voltage, current, and the brightness of light bulb depends on the number and arrangement of light bulbs in the circuit. So you have light bulbs, how the arrangement and number of them change different factors about the circuit, all about light bulbs. Now all students got the same learning outcome. For half the students in the unstructured condition, they only got this learning outcome in 20 minutes. The other half also got 5 pages of this scaffolding guidance that tells them what to compare, what to do. Now this was the best instruction we could come up with. It was with one of our instructors, one of the best instructors, Carl Weiland also participated in this in helping us shape it. PhET has a resource for teachers, and we took this as the most recommended activity, that's based on the most recommended activity in the PhET teacher website. And in fact, I wanted to do this in class study, and the instructor refused to do it in class because he didn't want to give just a learning outcome. He wanted to give these 5 pages to everyone. And these are pretty good. You build basic circuits, you take measurements, there are compare and contrast prompts, reflection prompts, and self-explanation prompts. It's going to use all the learning science in 5 pages. And then the trick was that we added a second activity about resistors. And this time everybody got a learning outcome again. The learning outcome was isomorphic to the original one, only about resistors and their arrangement. And nobody got scaffolding. So everybody got the unstructured version here. Now theoretically, theoretic students could transfer 2 things to this. One thing is transfer knowledge of how electric circuits work. The other thing that could transfer is the methods. Because to learn resistors, these are really helpful circuits to build. So ideally, the directive condition should be better here. Let's see what happened. And pre-test, because I come from Carnegie Mellon, so we have to test everything. So let's see what happened here. First thing we did, and I slightly oversimplify, we clustered students based on the pre-test. Now there's also pre-survey here about attitudes towards science. And there was also an experiences question about, did you take physics in high school? How many simulations have you played with in the past? And when we clustered students, we got very distinct clusters. And one cluster had very high knowledge. The other cluster had lower prior knowledge, but better attitudes towards science. And it's interesting. I do not show the attitudes here. You can go to the paper. It just came out, links later. I do not talk about the attitudes. I don't say that always high knowledge is low attitudes and vice versa. In this case, we had two clusters, one with high attitudes that they do not show but low knowledge, and the other with high knowledge and lower attitudes. So I'll refer to them as this. Now, in each of these clusters, we actually had roughly half the students in the red or the blue. So we have the higher knowledge directive, higher knowledge unstructured, and high attitudes directive and high attitudes unstructured. So this is what happened to the high knowledge group. Okay, and the tests are not the same. Everybody learned a lot. Everybody got several effect size improvement. Don't remember the numbers. It was different tests. For the high knowledge, red yield better learning than blue. So the directive worked. Okay, those who came with higher prior knowledge, getting these 5 pages, indeed generated better learning, right? As expected by the course instructor, for example. These 5 pages of scaffolding help students who came with the higher prior knowledge. For the other students, it didn't do anything. So for the other students, giving these 5 pages had 0 impact on their learning. And the other interesting thing that actually they learned pretty well. They were able to catch up, even though they started at much lower knowledge. Now when we look at transfer, there is no difference between any of the 4 of these. It's not significant. It's almost these two are slightly lower than these, but certainly no difference between these. So what we see here is a couple of things. One thing we see is that the scaffolding helps for the high knowledge, not for the lower knowledge. Students with lower knowledge did not benefit from the extra guidance. And nothing transferred. And in fact, what we saw in his note here, that the only thing that did transfer is slightly negative attitudes, because students don't like to be told what to do. So we kind of got not really helpful for the novices. So then we see, well, what did productive learners do? So we looked at the log files, and I'll just show an example. We actually did data mining over the entire 100 logs. We defined different actions students could do. They could construct or build, they could pause, or they could test a simple circuit with 1 resistor, 2 resistors, or many resistors. And this is time. So that's 200 seconds, so like 3.5 minutes here, or 4 minutes here. The students build 1 resistor and pauses, and then change a little bit, and then build some more. And now test 2 resistors, and build some more, and test 3 resistors. So we see increasing complexity. At this point, the student stops and goes back to 2 resistors and test a little bit of building and mainly pausing and thinking. And then some more of 2 resistors, and 2 resistors is a very basic circuit. And again, lots of pausing. So even though they did tons of actions, about 1,300 actions per student, or per simulation 600 actions, so every several seconds on average, you can see that the pauses are the most dominant action. Now the other thing that's interesting here, this is a very productive learner, is that this learner did only 2 resistors. And we see it very clearly. So what we did, I explained it to Ido earlier, and I will skip it now unless some data mining people who want to challenge me on that later. Essentially we can look, and we can do sequence mining, meaning we look at all the sequences, and we look at information gain theory. That means we look whether for the sequence we can learn something about the student. And that helps us identify typical sequences. The good learners tested very simple circuits. The unproductive learners, those who did not learn, they tested complex circuits. So actually testing the basic circuits was more conductive of learning. So what did we see here? We saw that guidance helped learners with sufficient prior knowledge, but the gains did not transfer to the next activity, and to the other students it just didn't matter. And we saw that productive learners tested basic circuits. So learners who succeeded to learn, who improved a lot from pre to post, tested most basic circuits. So, in other words, we gave the scaffolding we thought it was good. It was beyond their ZPD. It was too much for them. Good learners took one step back and tested simpler circuits. And then they manage to learn. If they can ignore the scaffolding, test the basic circuits, they learn. Well, but maybe just because the scaffolding wasn't good, maybe just giving them feedback on what we do would be better. So if we're so smart using log files, let's just give them feedback. And what about non-inquiry? The inquiry, it makes sense that they'll benefit a lot. What about more structured activities? So let's look at the help tutor. And let's work with Ryan, Ken, and Vincent. Ryan Baker, Ken Kettinger, and Vincent O'Leary. So this is a similar phenomenon, but in very different environments. So this is a geometry cognitive tutor, about 500,000 students a year, a system developed by Carnegie Learning of Pittsburgh. And again, we now have traces from all of the students, not like 0 traces. And this is a very constrained environment. Every problem is broken down to students. They do step by step, and they're kind of hit by a hammer. Whenever they get something wrong, they get red signal, and they can ask for very elaborate hints, and they can search a glossary, and they get feedback, not just read, they give them feedback text. Now, one important thing that this system has is that skillometer. Because we know everything about the students, we can estimate how well the students know each of the skills. So I can tell whether the student is knowledgeable or not that knowledgeable on different skills. And I want to focus on the help seeking. And we taught students to seek help. I'll show you in a minute how. Because what is interesting, students are really bad at asking for help. So one thing the students often do is they vastly underuse help. Okay, they always try again and again and not ask help. And I once asked a student who was clearly struggling, and I asked him, did you need help? He said, yes. I asked, if you needed help, why didn't you ask for help? He said, my dad told me real men never ask for help. Right, and that's reality, we have to deal with that, right? There's many gender, social factors about help seeking, as we all know, again, mainly from here. But the interesting thing is when they do ask for help, they abuse it, they overuse it. So once they ask for help, on 82% of the steps, they'll click all the way down to the most elaborate help. They won't even bother reading earlier levels. There are 7 levels of help, they can click next. On 82%, they'll take less than a second and they click to the last level. So it's going to vary by model. It's going to all or nothing at all policy. So he said, well, let's teach them to better seek help. So created a model of when students should ask for help. If they know what to do, they should try. If they don't know, they should ask for help. And if they try and get it wrong, but they know how to fix, they should fix, etc., etc. Don't talk about that. Yeah, there's a paper for that, or we can talk later. And then we kind of build a model that uses the help model, the domain model, to give students feedback. And this is how it looks like. The student tries a step, and I think that they don't really know them, because I can estimate skill level. Perhaps you should ask for a hint. This step may be difficult. Give them a blue message without knowledge about geometry. Just tell them ask for a hint. Now they're going to click through. So if they click through and don't really read, and now they start clicking through, it says, hey, try to take more time to read the hint. So we gave them feedback. We thought that was a huge success. I still think it was a huge success. Because the model predicted post-test better than pre-test. So our model of help seeking was better predictor of learning than incoming knowledge, which is not often the case. We had reduction in help seeking errors, is clicking through or avoidance. Also in future learning without feedback. So we just measure what they did later without the blue messages. And they did better. We also had paper measures of help seeking. They had hints covered with stickers on paper. And we actually saw improvement on paper too. The only thing we didn't see is learning geometry better. They did not learn geometry better. So again, we gave them guidance in supposedly the best way. They got tailored hints to them based on an elaborate cognitive model that estimated knowledge level. And all this together, we couldn't improve learning. So are we wrong to think when students use help? So here's how we tested that. Let's assume that each problem, move the cursor to the side so it bother us. It's dead. Each problem is associated with a skill. Right? Skills can be angle addition, angle subtraction. Let's call them square, triangle, circle, and square. And on the square, let's say the students get it wrong, ask for help, then they get it right, and they get triangle right, they get the circle right. Now, what will happen on this square? What will happen? Remember, they got this square wrong. So if they haven't learned, it will be the same. Based on what they did in n, we can evaluate whether they'll get n plus 1 better. So this is an opportunity for a logistic regression model. Essentially, logistic regression models are binary models that predict success or failure, 1 or 0. So we can predict success on new step based on previous step of the same skill. So I can look at whether what they did here was productive for learning. Why is this interesting? Because this is a within student measure. You can see whether what the students did on the step before will help them learn the next step. And students do different things. So I can evaluate different strategy here and see which of the strategies here was good. One that uses help or one that avoids help. And I correct for student factor, the skill difficulty, and that is a full model that I'm going to get into detail now. The interesting thing that's a property of binary and logistic regression models is they predict log odds, which is a tricky mathematical concept. One way to interpret log odds is, let's say we have a baseline of 50%. So with a baseline of 50%, how will this change if students behave a certain way? Okay, so now again, we have the cognitive load alarm. I'll walk us through the table slightly slower. As I said, the cognitive tutor estimates student knowledge level on each skill. So this is when the cognitive tutor estimates, that should be high with the GH. The system estimates that the student knows this already. Medium skill level, or the student does not know it. Okay, and again, the same student transitions. It's a mastery-based system. Students start not knowing, with practice will get to medium, with practice will get to high on each skill. What happens when students ask for too much help? Asking for too much help is always bad. If the basic chance is 50%, and you ask for too much help, this chance goes down to between 8 and 20%. So too much help is bad. What with too little help? So guessing too much. For the high skill, when you know what you're doing, it doesn't matter whether you're guessing or not. It'll be fine. For the medium skill, guessing is bad. It goes down from 50 to 31. So when you know a little bit, you better ask for help, because avoiding help is not good. But for the low level, avoiding help was good. So in other words, what we see here is students of low ability on these specific skills benefit more when they avoid help rather than when they use for help. Now to be clear, we define guessing as quick attempts that were the wrong answer. So students still got it wrong. Right? Remember how we moved from step n to step n plus 1? They guessed, they got it wrong. But even though they got it wrong, it improves their chances from 50 to 69 on the subsequent step. So we kind of see a pattern like before, that too much guidance is always bad. But on new step, on new skills, guessing may be productive. Now once some knowledge is acquired, you become the medium skill level, then get some help. But before you know what you're doing, just try for yourself. And an analogy they often give is actually when people come to Vancouver and they'll ask me, let's say, how to go by bus from SFU to UBC, the two universities. The answer has a lot of domain knowledge. It will be, well, you get a compass card, you board the SkyTrain, you then move to the B line. Now, none of these actually appears as clear signage, right? Compass here or B line. B line actually is 99. I don't know why 99 is called B line. But if they went lost in Vancouver a couple of times, right? They went lost, but now they understand the instruction. Now they know how to board the SkyTrain, they know how the Broadway station looks like. So there is value in being lost. We learn vocabulary, we learn operators, we get some experiences that help us. And this is where actually Dewey said it much better than me. He said failure is instructive. And Dan Schwartz, that Doris threatened me not to mention him because he's across the bay with the bad guys. He has a paper that I think not enough credited. And this is a 2007 paper called Reconsidering Prior Knowledge. And that's what he says about prior knowledge. He says, we propose a different approach to prior knowledge. We shifted the focus of instruction to help learners develop early knowledge that they did not already have. Our proposal is that noticing and reconciling I can never say this word, incommensurables prepares students to understand canonical solutions when given an opportunity to learn. So he defined this early knowledge. Early knowledge as experiences that help students learn from instruction. So that's what we need to do, right? In an earlier work, Dan and John Bransford call it we're creating time for telling. So students first get this early knowledge, and that helps them learn better. Which brings us to the third example of invention activities from Dan Schwartz and productive failure. And this is work again with Ken and Vincent, and also Doug Bond and Natasha Holmes from UBC, and Katerina Leubel from Freiburg. So the concept of productive failure, I don't know, was Manu here? It is not yet. I'll define. Concept of productive failure says that some form of problem solving prior to instruction is helpful, even when students fail. So it says, let's give students activities, carefully designed, not just any activity. Let's give students some activities. Have them work through the activities. They may fail, but that's productive failure, because thanks to these activities, they will better learn from subsequent instruction. So we don't go to the dichotomy of instruction or discovery. We combine them. First, you just try to discover. When you fail, you get instruction. But the failure helps you learn. So Kapoor calls it productive failure. Dan and Taylor Martin talk about invention activities. Students try to invent, and I'll show you in a minute how he's doing this. And we just did a nice meta review on all the studies. It's kind of nice, and the concept. And I think it's kind of realistic, right? Like, let's say you get a new phone. And how many of you will go to the manual where it says play with the phone first until they get stuck? So you can say, let's do the same. Let's play with the phone before we get stuck. Or let's have students play with the concepts before they get stuck. Only them will provide instruction. Kurt Van Leen called it impulse-driven learning. So my thesis in the last half an hour has been, well, students need to try their own thing. In the help tutor, the geometry tutor, when they try their own thing, they learn better. In the physics simulation, when they try their own thing, they learn better. So is here too, do they need to try their own things? Or is it enough to see failures or to experience failure, but not of their own thing? Failure of other things. So we did the following. We created this system. And students were tasked with creating a measure of consistency. These are middle schoolers, and they don't know yet a formal representation. I'll show you in a minute how this works. So we say create consistency. Essentially, they create a method like point, minus point, then I'll add another step with point, minus point, then average them. There's not much notation here. It's more thinking in steps that emulates the way we saw students solve these problems in think-aloud records. So first, they rank. They see two examples here, and they rank them. Which one is more consistent? This one is more consistent in this case. Then they create a method, and then they evaluate whether the method they created is correct or not. And these two examples are contrasting cases. And we kind of did a fancy AI engine here that analyzes the student's method in real time. And it creates in real time contrasting cases to challenge their methods. So when students will get this method, usually what they'll do is range. So well, these 2 points are further than these 2 points. So if they'll do range, the system will generate these two sets. Aha, same range. Which one is more consistent now? That's what the system does. I think we have a short demo. Yes. Now what I want you to see in this demo, this is real time. Here at the bottom. I'm going to speed it up about 10 times. And what you'll see is how little they work in the first 3 minutes, and then they work in bursts. Just like we saw with the physics college students. It's all in the pauses. Again, right, that's about 10 times fast. We're about 30 seconds in, 40 a minute in. They work in pairs. They talk with the mouse, because people talk with the mouse, so that's gesture right there for you. And then finally, after 2 minutes, they ranked, said A is better, take another minute. And only, I slow down the speed, we're about 3 minutes, now they start working. And look at the speed of how they work to create the method here. And now they do the other side. They do about 200 actions in these 2 minutes. And they finished about 5 minutes. Finished a second too late. They finished about 5 minutes. The method does not work. So the method does not work, but they take until 9 minutes and they have another burst of activity. So we gave 2 conditions to students, right? I want to see whether it's about pursuing their own errors. So half the students, we had 2 levels of middle school classes. It's in an inner city school in Pittsburgh, 80% free lunch. We had the advanced classes, which are kind of pre-algebra, and we had the basic classes, which are very basic arithmetic still. And they had 2 conditions that are not shown here. One condition came up with their own methods. The other condition got examples of methods and we're told, here, test these methods. Because if it's about failure, let's give them good methods to fail with. We actually gave them the best methods that highlight the features, such as one method didn't control for sample size, another method didn't control for positive or negative distances. We gave them really good methods to fail on. So again, from the self-explanation literature, erroneous examples literature, solved example literature, we would expect that giving them good methods will help them what doesn't work, more than just pursuing their own thing. Now, when we look at normal measures such as procedural, conceptual, no gap, but we also look at that consistency series of studies, debugging items. Debugging items give them wrong methods. For example, here you can see that the first step is average. Second step just takes one gap instead of all gaps, and then divide by n. So that only looks at one gap instead of all the gaps. It's a crappy slide. Only one gap instead of all gaps. And what we see for both the advanced and the novices, we see that those who invented their own method performed consistently better. And we actually have studies at the college level that show similar gaps several months later. So it's really far transfer. So inventing your own methods leads to better learning than evaluating existing and very carefully designed methods. So again, there is something about this exploration, about me doing my own thing. Now, the interesting thing here is that this is fairly empowering. So here's a recording of students. They worked a lot, fairly elaborate methods they got. And they got these 2 sets. And they didn't manage to solve these 2 sets because there is a repeated point here, repeated value. And that really confused them. What should they do by repeating value? You know one of them, calculate distances twice, do everything here. They did, so they tried different things. And they were stuck on this for close to 10 minutes. And because they kept getting 1.6 and they wanted something here, I don't remember what. So let's see how, let's hear them when they actually figured it out.
Yeah. Yes. All right. That's hard with that.
Right, so I have students say that's hardcore math there, oh that is so cool. About math, these are 11th graders by the way. And so yeah, because their value, this value is lower than that value. By the way, their method is completely wrong. Right, but that doesn't matter. They took out what they had to, they had a puzzle, they solved it. So, trying to bring some things together, that was really, only now I see there's a timer, and that was a bit fast. Okay. In the labs, what we saw, guidance only works with sufficient knowledge. Without sufficient knowledge, the guidance didn't work, and it didn't transfer. And productive students ignore the guidance, explore their own questions. In the very different geometry tutor, Students with low prior knowledge learn better when they guess rather than ask for guidance. As they gain practice, guidance helps. And students learn better in the Invention Lab when confronting their own preconceptions. And they value doing so. We have data. You know how, I don't know how schools here work. In Pittsburgh, sometimes there are like double blocks with 2 minutes in between. And it's real, so we just measured how many students in different conditions stayed during these 2 minutes in. And students who had to invent their own methods, about 30% of them stayed in. So 10 students in a class of 30. And students who just had given methods, 1 student out of 30 stayed, right? So 1 versus 10, again, consistently across classes. So, what do I learn from this? Instruction should support what Dan calls early knowledge prior to guidance, to facilitate exploration. And that means designing, the instruction should design relevant affordances, constraints, and feedback. But what I kind of wiggle here and didn't really focus on, what did this environment offer? But the physics simulations offer these very intuitive changes in light, and you see kind of magic school bus, you see the electrons flowing. Without that, it doesn't mean much, right? Mitch Nathan talks about situational feedback, the ability to extract feedback. We need to design the right affordances. Why? We need to help learners build relevant vocabulary, intuition, and appreciation of that. I also think about it, when we just give them a black box of knowledge, they don't know what to do with it. This exploration, they make room on the bookshelf. And also identify the right bookshelf. Say, oh, that's a consistency bookshelf. I actually don't know enough about it. Let me make some room for a new book with the right connections. And one interesting thing here is that this is actually consistent with cognitive load theory, at least my read of cognitive load theory. Because when students don't have sufficient knowledge, then guidance imposes cognitive load. Now, the cognitive load theory talks also about goal specificity. Swirler talks a lot about how novices should just be given environments to figure out their own goals. And that's essentially what we're doing here. Right? I'd argue that exploration, yes, is cognitively overloading, but that's a good example of cognitive overload. And an example of this is an image of the background here that actually are not relevant. I just, on the cab here, I realized, hey, I need to change all my background to this. It was Charlie Chaplin earlier. And the reason is I realized that these are people who do whatever they want to do with the scaffolding. Right, the scaffolding is not there to have lunch. But what they choose to do with that. And I think that's kind of also what our students do. They choose how to engage with what we give them. So probably rather than try to enforce our way of interpreting the questions, it may be beneficial to help them explore their way of engaging with the materials through the right affordances and constraints and feedback. And that's about it. Thank you.
Questions for Ido?
This sounds to me so the difference between exploring yourself and finding your own method versus following someone else's method is a little bit like the difference between looking at correlating variables versus manipulating and looking for causal relationship. So you cannot figure out a causal relationship if you just observe variables, but you can if you can intervene and manipulate. Just thought that I don't know if it's.
Yeah, I need to think more about it. My gut reaction is that it's a lot about. I'm tired of saying prior knowledge activation, because prior knowledge activation is the answer to everything. But I think that what we do when you explore your own is you kind of get rid of something that suits you, right? Where you have to express it and see whether it works. You may assume that you know everything, or students assume they know everything. So there's something about the ownership that helps them let go. So I think that I actually think that there's a big attitudinal and non-cognitive element here, and that's why the students were so happy versus just seeing this video, even if you understand it. So one thing is how to understand when it's not yours. But I think it's a lot about the ownership. So I actually think that it's the attitudes that make a big difference here. But I'm yet to explore this too deeply. But I need to think about it. So.
Maybe the ownership is important because you want to have control and you want to find out the causal relationships.
Well, for example, I mentioned the invention work. I'll just go one slide back. I'm not going to do that. Yes, do that, sorry. So we have this slide. Here, everybody used the system. The question was whether you use your own ideas or whether you're given a sheet with ideas. Here, everybody uses the same simulation. You're just instructed which circuits to build versus you could build your own circuits. So in all cases, you did manipulate and observe the outcome.
I have a question that slightly dovetails on that, I guess, and it's about the students who are exploring with little to no guidance, just trying to figure things out. You earlier gave the analogy of a person who's sort of lost in Vancouver. One of the worst places to be lost.
It's actually a good place to be.
Yeah. And I wondered what you do with the telemetry of people as they're exploring. What can we learn from that, both for specific learning environments and perhaps more generally about the nature of what it is that we do when we're lost?
Okay, so there are two answers here, none is satisfactory. One is that this is actually, I had this morning a meeting exactly about that. We try to define productive exploration. And at some very basic level, we know what it means. It means that we know what it means, and at the same time, it's kind of boring answer, so we're not too happy. We see that there is some systematicity. So let's say the simulation, you need to try all the variables, so you need to change the voltage of the battery in order to learn. So let me take one step backward. We see three types of exploration. There's actually first learning the interface. And this is to me learning the operators. I talked about gathering and learning operators and vocabulary. So that's exactly the operators. I learned, I can change the slider on the battery. And then that helps me later to follow guidance, right? Reduces cognitive load later, I get vocabulary early. Another thing is that, so we see first you explore the interface, then you explore the domain, so you'll wiggle things to kind of get qualitative relationship. And sometimes you'll explore again at the end to look at interesting interaction effects, etc. So after you did more measurements. But it's hard, we're not doing a very good job at exploring, detecting good exploration. And I think the reason is exactly because people have their own ideas. And that's the other answer. There is this, so I don't know how many of you read Anna Karenina. It's a fantastic book. It's pretty heavy, worth it. And it has one of the most famous opening sentences. Do you remember it by heart? Something like all happy families.
Similar.
Exactly. All happy families are similar to each other. And all miserable families, each miserable family is unhappy in its own way. And to some degree, we see this here. Once you start doing the structured inquiry of, I'll change one thing at a time, etc., we see a very clear path to success. So all happy family are happily in similar ways. The exploration phase, which you're still slightly more unhappy with, we see huge divergent thinking. So I mentioned to you earlier, we're actually studying now scientific creativity because exploration invites divergent thinking. So how can we find patterns in divergent thinking? That's a good question. So at the very low level, what we do with the telemetry you ask, we just essentially group learners to productive, unproductive. That's one thing we do. And we see what patterns come up. Another thing we do, which is tons of fun, I have on my desk sitting 200 graphs, like the graphs I showed you before with the circuits. And we apply, we do thematic analysis. I'm trying to sit where 5 of us, we sit and we try to code them. And it's a lot of fun because like I don't come from a background in qualitative work, and applying qualitative methodologies to telemetry or trace data is really fascinating for me. So I'm not sure we'll go for this, but every week we have 2 hours where we just sit and we code these graphs. So I'll be wiser in several months, hopefully.
I have a question in regards to age. So in the studies, did you notice any correlation between the age of the student and their willingness or desire to explore?
So, yes, this is so interesting, and I guess that you suspect that indeed older students are more resistant. We have huge problem in the college classes, especially at UBC, because it's a pretty good school, kind of like here. So students who come there are, the students are used to be the best and never be wrong. And now we tell them, hey guys, well, we have the language about every answer is correct as long as you can justify it, whether or not, and then we show everyone is wrong and we use the word failure. There's tons of work, I didn't put it here, but tons of work on creating safe environments. And it's a really challenge. We show them at the beginning of class results from these studies to convince them that that's good for them. And to some degree, the attitudinal shift towards, hey, failure is good, that's part of what they wanted to learn. Huge problem, we're still really bad with this, we'll still have students who'll say, we'll have students who leave class and say, I still think that what I did was right, regardless of what we do with them. The most interesting thing was I mentioned how the younger inner city school students in Pittsburgh loved it, mainly the lower ability students. Because finally, everybody was wrong. Right? They used to being wrong all the time, and now they have a teacher telling them it's good to be wrong, so they loved it. The older we get, the harder it gets, and that is a true challenge. Yeah. So all this was cognitive work. All the attitudinal work at the background, and then attitudinal measures, we're only starting to scratch that surface, and there's tons of work to do there. I don't know anyone who's actually doing this. Doesn't mean it's not done, maybe it hasn't read enough, but I don't know.
There's another hand there somewhere. Well,
Okay.
then, thanks again. Thanks so much for talking.
Thank you guys.